Good afternoon, class. We are looking at Chapter 2 Limits. Here's Section 2.1, Limits of Sequences. Chapter 2 Limits, we cover 2.1 Limits of Sequences, 2.2 Limits of Functions at infinity, 2.3 Limits of Functions at finite numbers, and 2.4 Limits, algebraic method. So first, reminding everyone of what we have covered, Section 1.6, here's the summary. A sequence is a list of numbers written in a specific order, a sub 1, a sub 2, all the way to a sub n, first, second, and nth term. A sub n is the general term, and n is the set of positive integers, 1, 2, 3 to infinity. Recursive sequence, also known as difference equation, is in the form of a sub n plus 1 is f of a sub n. The next term depends on knowing the previous one or previous ones. An example would be a Fibonacci sequence, where f1 is 1, f2 is 1, and then f sub n is f sub n minus 1 plus f sub n minus 2. That means if you want a term, add the previous two terms. So you write 1 and 1, and then add them up, you get 2. Add these two, you get 3, and so forth. So if I want the next term, all I have to do, add these two, and I get 34. Arithmetic sequence, we have a common distance. Therefore, a sub 1, a sub 1 plus d to infinity, and recursively, a sub n plus 1 is a sub n plus d. Explicitly is a sub n equals a sub 1 plus n minus 1 times d. Geometric sequence, we multiply by a common ratio, a sub 1, r, and so forth. Therefore, recursively, a sub n plus 1 is r, a sub n. Explicitly would be a sub n equals a sub 1 or to the power of n minus 1. Now, limits of sequences, and here's the summary, section 2.1, the summary. Limit refers to the long-term behavior of a sequence, i.e. what happens to a sub n of a sequence in the long run. Lim means limit of a sub n as n approaches infinity equals L. We say that a sub n converges to L. Limit of a sub n as n approaches infinity is infinity, or limit of a sub n as n approaches infinity is negative infinity, or DNE does not exist. We say that the sequence diverges. To find limits, simply plug in the value and observe. Couple of theorems we want to look at. The limit of r to the power of n as n approaches infinity depends on the value of r. If the value of r is between 0 and 1 here, and in general between negative 1 and 1, this goes to 0. It's 1, it's 1. If it's 1, it's 1. If it's larger than 1, this goes to infinity. This is a very important theorem we should know. An example that can be helpful is this. If I said, let's say 1/3 to the power of 2, I get 1/9. To the power of 3, I get 1/27. And it's becoming smaller, but 3 squared. So this is referring to this part. 3 squared is 9, 3 cubed is 27, and so forth. And this refers to this part, it's getting larger. Therefore, the limit of r to the power of n as n approaches infinity depends on the value of r. If it's between negative 1 and 1, ultimately goes to 0 because it becomes smaller and smaller. If it's 1, it's 1. And if it's larger than 1, the answer is infinity. The limit of 1/n to the power of p as n approaches infinity is 0, where p is positive. Remember, if p is negative, comes up, becomes negative. That's why we keep it as positive. And what this means, if you're dividing a number by a number that is getting larger and larger and larger, the fraction getting closer and closer to 0. That's the meaning. Geometric sequence, when we add them up, we call it geometric series. So the summation of a or to the power of n minus 1 from 1 to n is a plus a sub r all the way to a sub r to the power of n. It becomes a times 1 minus r to the power of n over 1 minus r. That's the series. That means the sum. And if r is between -1 and 1, what happens, everybody? According to this goes to 0. So you get a over 1 minus r. With the geometric sequence b sub n plus 1 is r b sub n, and the solution is b sub n equals b sub 0 r to the power of n. By the way, in some texts they use this, in some texts they use a, and it's the same as what we wrote in the previous one, which was we had a sub n equals a sub of 1 or to the power of n minus 1. They all mean the same thing. We are looking at it from different points of view. B sub n plus 1 is r b sub n plus c. I hope you remember when we dealt with patience, when we add a constant, then it becomes the same thing plus this piece. And I have the proof, by the way, at the end of the PowerPoint, if anybody's interested. We will look at this as we look at examples. Here's the summary, everybody. And you can replace the A with B sub 0. It's important to know that we do that. Now, let's actually look at an example here. What happens to A sub n in these two cases? Part A sub n is 1 over n. So you plug in, and I hope you see that if I plug in everybody, first I get 1 over 1, which is 1, then I get 1 over 2, then I get 1 over 3, then I get 1 over 4, and it's getting smaller and smaller. By the way, 1 over 2 or 0.5 are the same, so it's getting closer and closer to 0. And we can observe that the limit of 1 over n as n approaches infinity is 0, and therefore it's convergent. Reminding you of this, and I hope everybody can see that in this case, P is 1. Okay, everybody? If you were to graph it, it looks like this. Also, I want to remind you of the function y equals 1 over x. That's what you dealt with in algebra as far as the graph of this function. If you recall, it looks like this with the horizontal asymptote, which is the x-axis, y equal to 0. And that's exactly what this one indicates. Again, I'm connecting this to algebra and rational functions and their graphs that you've seen. I hope it's coming back to everybody. Let's look at part B. So I'm going to erase this part. Now, if I choose n to be 1, I get -1. And if I choose it to be 2, becomes +1. Meaning, if I choose n to be odd, I get a negative number. Even, I get a positive number. And this thing continues. So the value is always between the two. It's either -1 or +1, and it alternates, which means the limit does not exist. And it makes B sub n a divergent sequence. Convergent means you have to come up with a specific number, one number, and one number only. And so if you were to graph it, notice those are the numbers. They oscillate between -1 and 1. So the limit does not exist. Sequential limits. A sequence A sub n has a limit L, and we write let A sub n, A sub 1, A sub 2, all the way to A sub n be a sequence and L be a real number. We write the limit of A sub n as n approaches infinity is L if we can make A sub n arbitrarily close to L for all n sufficiently large. We also say A sub n converges to L. So when that happens, if A sub n and B sub n are convergent sequences and C some number is a constant, then the limit of A sub n plus B sub n as n approaches infinity is equals to limit of A sub n over as n approaches infinity plus limit of B sub n as n approaches infinity, means the limit of the sum is the sum of the limits. The limit of the difference of the limits. If you have a constant, take it out. The limit of the product is the product of the limits. The limit of the ratio is the limit of the ratio of the limits. Denominators can't be zero. And they're very straightforward, class. You'll see how we apply those in a moment. And of course, reminding you of this theorem that was mentioned. The limit of 1 over n to the power of p as n approaches infinity is 0 as long as p is larger than 0. If p is larger than 0. Okay. What about this one? We write the limit of A sub n as n approaches infinity is infinity if we can make A sub n arbitrarily large for all n sufficiently large. Finally, we write the limit of A sub n as n approaches infinity is negative infinity if we can make A sub n arbitrarily negative for all n sufficiently large. In both cases, the sequences diverge in the last two cases. All right, let's look at this example. Again, I'm reminding you of the theorem that we have seen. There's nothing brand new here. How do we get the limit of 2 to the power of n minus 1 over 6 to the power of n as n approaches infinity? We make up two fractions. So 2 over 6 is 1/3 to the power of n, and this one, so this one is 1/3 to the power of n. I can put an n here because 1 squared is 1, 1 cubed is 1, 1 to the power of n is 1. So I get the following. Limit as n approaches infinity of 1/3 to the power of n minus 1/6 to the power of n. We use the limit laws. We make up two limits. The limit of the difference is the difference of the limits. Now, what is 1/3? What is 1/3? We should know this one. Each one is 0. The answer is 0. This is a very important theorem. We should know it, and we should be able to apply the limits. Okay. Again, you don't have to write these questions. You have all of them. We just go over the solution. So we want to find the limit of 2 to the power of n as n approaches infinity. So what do? Remember, to find limits, simply plug in the value and observe. So plug in. What is 2 to the power of infinity? Take a look. If r, the base is larger than 1, is what? Infinity. It diverges. What about this one? Let's plug in. 2 to the power of negative infinity according to exponential rules. A to the power of minus m is 1 over a to the power of m. I hope you remember that from algebra. If you have a negative exponent, you just move it. For example, if I had 1 over b to the power of negative n is the same as b to the power of n. So if you have a negative exponent, you just move it. So this means one over 2 to the power of infinity, which means 1 over infinity, which means 0, and therefore it's 5 plus 0 or 5, and it converges. Again, this is a very important theorem we should remember, and this also we come across a lot. Part C, plug in. And of course, 1 over infinity, it's really using this one where, remember, where p is, in this case, where p is 1. And so 1 plus 0 is 1, and it converges. So very straightforward. A quick recap. This one, 2 to the power of infinity, infinity diverges. This one, to the power of minus infinity, or 1 over 2 to the power of infinity is 0, 0 and 5 is 5, converges. This one, 1 over infinity is 0, 1 and 0 is 1, converges. What happens here? What are we dealing with here? This, if you plug in, by the way, you get infinity over infinity. What you're dealing here is called a rational function. So you're dealing with a rational function. N is approaching infinity. The technique is to divide by highest degree term in the denominator. That's the technique. And everybody, division by n squared is the same as multiplication by 1 over n squared. So if I'm dividing by n squared, this becomes 2, this becomes 5. This becomes 3 over n minus 1 over n minus 1 over n squared plus 8 over n squared. As you can see, this 3 over n, this one, each one of this goes to 0, everybody. When you take the limit, the final answer is 2 over 5. So when you're dealing with a rational function, that is the technique. So for this question is exactly the same thing. You're dealing with a rational function. By the way, even if n approaches negative infinity, which we don't do it for this course, for sequentials, it's the same technique. You divide by highest degree term in the denominator, namely n squared. So you divide by n squared. This becomes 3 over n, this minus 1 over n squared. This is 7, this is minus 3 over n. And this one, and this one, because n is approaching infinity, everything goes to 0 except 7. And it's important to note what you're dealing with here is 0 over a number other than 0. Therefore, the answer is 0, because later on we discuss 0 over 0 is indeterminate, is a difference. What about this one? Again, rational. Rational means the top and the bottom are both polynomials. So n is approaching infinity, divide everything by n. The highest degree term in the denominator. Simplify. And if you plug in, remember in all of these cases, we plugged in that we ended up with those. If you plug in this is infinity, this is 2, this is 0. And infinity over 2 is infinity. Infinity over any positive number or times any positive number is infinity. Square root of infinity is infinity. Infinity divided by 10,000 or 10 billion is still infinity. The only thing you want to be careful, if it's infinity divided by any negative number, it ends up being negative infinity. That's the only thing you want to be careful of. So let's recap. All three questions, we are dealing with rational functions. All of them, and is approaching infinity. The technique is to divide by highest degree term in the denominator in all cases. Okay? Calculate the first 8 terms and find the limit. The first term, a sub 1 equals to 2. Then a sub n plus 1 is 1 minus 1/3 a sub n. That means if you want a term 1 minus 1/3, the term before that. Since I have a sub 1 now, I want the second one, a sub 2. If I want this to be 2, then this must be 1. So you plug in. Replace the a sub 1 with 2. 1 minus 2/3. 1/3 is the answer. What if I want the next one, the third one, then this must be 2. I hope you understand this concept, everybody. Okay. So a sub 3 is 1 minus 1/3 a sub 2. Replace it. We get 1 over 9. 1 minus that is 8 over 9. And so we have those. Now we can continue and get the rest of it. What I want you to notice, it takes a little bit of a time to do the rest of them, okay? But we proved we can get them. It's not a problem. So if I want a sub 4 is 1 minus 1/3, a sub 3, so on and so forth. But what I want to show you is that, okay, when you get this far and you've shown those two pieces, and you may come across a question similar to that on your homework, you may use a calculator, it's fine, but you really have to do at least 2 of them by hand. So how do you use a calculator? The very first term, whatever the number is, you put it into a calculator and you say a sub 1 happen to be 2, store it in x. And then this term, if the limit exists, the limit is L, or in the case of a calculator, X, so this can be replaced with X, this can be replaced with X. So you put 1 minus 1/3 X into X now. Again, why do we do that? The limit is X, so 1 minus 1/3 X is put into X. And notice 2 is stored in X, 1 minus 1/3 X is stored in X. And you get 2, you get this number. Please understand 1/3 is 0.3 bar. 8 over 9 is 0.8 bar. So notice that. And you keep on just enter, enter, enter. And you have those numbers. You put them here. I'm assuming this part, you can look at it again if you have a graphing calculator, or I've shown you how to, come up with a graphing calculator online for free. You can try it. You don't have to go this route. This is just to speed up the process, everybody. Now, when you come this far, you may recognize because of this, the sequence converges to 0.75. If you don't, You can calculate a couple more, and for sure you'll see that. Here's the reason. Because one might say, okay, 0.74 went up to 0.75, went down to 0.749. I don't know what the limit is, so you need to do a couple more. That's fine. But I'm going to show you algebraically, and I'm going to prove to you the answer is 0.75, just the way I did the last question of the previous recording when we came up with A over K. Here's how you have to learn in case you do it analytically. So we start with the given. The given is A sub n plus 1 is 1 minus 1/3 A sub n. This is given, right? This was given, right? So we are going to rewrite it. So the limit of the left is equal to the limit of the right as n approaches infinity. And the limit of the right is the limit of this number minus 1/3 limit of this number. This is 1. And this is minus 1/3 limit of A sub n as n approaches infinity. Now, what I want you to pay attention to is this. This piece, everybody, and this piece must have the same limit. If the limit exists, please understand what happens. This is a term after this one. At some point, things do not change. That's the concept of a limit. At some point, the numbers repeat. So that's why we used x and 1 minus 1/3 x here. Normally, we use L. So if we call it L, so this I'm going to replace with L. This is obviously 1, and this is minus 1/3 L. If I move this one to the other side, make it plus, we get 4/3 L. And if I multiply by 3/4, I get L equals 3/4. And please know that 3/4 and 0.75 are identical. So I proved that the answer is 0.75 algebraically, and you can do the same, everybody. So the process is what you see here, and you can prove it algebraically. As far as the calculator part is concerned, you can put 2 stored in X let's see, 2 stored in X. Okay. And then 1 minus 1 divided by 3 X stored it in X now. Enter, and we got this number here. 0.334 here. So, and then if you press enter repeatedly, you get the next one, and the next one, and the next one. And this is it.